Hi everyone, bonjour. The IB Crocodile is here. Welcome to my YouTube channel. Let's have a look at this question in paper 1, past paper, IB Physics, time zone 1, in May 2023, question number 5. A ball is projected at an angle to the horizontal on Earth, reaching a maximum height h and a maximum range big R. The same ball is projected at the same angle and speed on a planet where the acceleration due to gravity is 3 times that on Earth. Resistance effects are negligible. What is the maximum range and maximum height reached on that planet? Okay, so comparing, of course, with R capital and H capital on Earth. So obviously, this is a projectile motion question, right? So let's review the facts that we know about projectile motion. Okay, so first of all, the initial velocity as a vector, according to the question, makes an angle theta, right? So let's call this U, right? And let's say, okay, there is an angle theta with the horizontal. So in projectile motion, we always divide the kinematic equations into 2 directions, vertical direction and horizontal direction, right? So yeah, we have U as a vector, as a velocity, initial velocity makes an angle theta. So what would you do? Say, okay, so I have horizontal component Ux equals to cosine theta, right? And the vertical component of U is going to be sine theta. Okay, this is the first fact, that let's say Uy equals to U sine theta. So this is the first fact and the first step you always do when you approach a projectile motion question. The second fact, the horizontal velocity is always constant all the way, assuming, because the resistance effects are negligible, so assuming no air resistance or ignoring the air resistance, so horizontal velocity you can take it as constant all the way. While the vertical velocity will be, of course, affected by the gravity, by the acceleration due to gravity. So the maximum height, which we are going to find out now. So in the vertical direction, we're gonna use kinematic equations of motion because we have gravity, right? And let's just talking about vertical direction of the motion. So let's say this is h. Okay, now also the third fact, at the maximum height, the final vertical velocity is 0, but still we have a horizontal component here, still constant all the way. So at the maximum height, there is a component of the of the horizontal velocity, but the vertical velocity or the vertical component is 0. Okay, so now let's apply one of the equations. So let's say v squared final velocity equal u squared plus 2as, right? Now at the maximum height, I'm going to replace it by 0. The v equals 0. Now u, which is the vertical initial velocity, which is u sine theta in this case, all to the power of 2. Now acceleration here is going to be g, and it is negative because going up against gravity. So let's say, so basically negative 2g, I'm going to call it g sub e, and then I put s, or the vertical displacement, h, as the problem here called it. Okay, so now we can actually solve for h. Okay, so we can say, okay, 2g sub e times h equals to u sine theta all to the power of 2, implies that h capital is going to be u sine theta all to the power of 2 divided by 2g sub e, and let's call this equation 1. Now, what is now on the planet? On the planet here, we have the acceleration due to gravity is 3 times that on Earth. Okay, So by applying, and then of course he says here the same speed, the same angle. So we have the same u, the same theta, did not change, right? So now we can say, okay, so the h on the planet is going to be u sine theta all to the power of 2 over 2, and instead of g sub e, I'm going to replace it by 3 times g sub e, right? Or basically the g sub p, or g of the planet, is 3 times g sub e. And let's call this equation 2. Now, if you compare the equation 1 with equation 2, you see this whole term here is there divided by 3, right? So that means we are in between A and B. So I can cross off, the answers C and D. Now the range. Now what is the range? The range in projectile motion is the horizontal distance. Okay, so the range is basically the horizontal distance here, right? We call it the range, which is R capital. Now, the way to get the range, we're gonna use the horizontal motion. Now, horizontal motion is easy. Why? Because the speed is constant. The horizontal speed is constant. So you can say, okay, ux, right, is equal to the distance over time. Horizontal distance over time, which is R over the time of the trip, the total time of the trip. Okay. So now we need to find the time of the trip, in both cases, and compare and see what is happening in the range, right? So actually we can say, okay, so the range here, like let's say R on Earth is ux times, the time, let's say T1 or T sub E, let's say T sub E, the time of the trip on Earth. Okay, and let's call this equation 1. Now, to find the time of the trip, you may find the time, to the maximum height, and then double it, because you can see here a symmetry, right? So we always do 90% of the cases, we can actually find the time of half of the trip, or basically the time to reach the maximum height, and then multiply that by 2, so you get really the time of the trip. Okay, so in this case we can use another equation if you like. So at the maximum height, again, v equal, let's say, u plus at, right? Now v is 0 at the maximum height. Now u is, okay, let's say uy in this case, of course, because we talk about gravity. So uy, which is u sine theta, doesn't matter because here u and theta are the same in both planets and Earth. And then negative minus gt, right? Because negative g, because going upward again is gravity, so the gravity g has to be minus. Okay, so that implies that u sine theta is equals to gt. That's the time to reach the maximum height. Okay, so t is u sine theta over g, right? So therefore the time of the whole trip on Earth is going to be 2 times u sine theta over g. Makes sense? Because here we have the time to reach the maximum height where the velocity equals 0, right? So I got that using this kinematic equation, right? So I got here t equal u sine theta over g, but then the time for the whole trip to find the range is basically twice that time. So t sub e is 2u sine theta over g. Now u sine theta are the same, u and theta are the same on the planet. So t sub p is going to be 2u sine theta divided by 3g sub e, because again g of the planet is 3 times g on Earth. Okay, so the time, okay, and ux is the same. So basically we can say R on the planet, let's say R on P, is going to be ux, which is the same, times TP, right, which is basically ux times t sub e divided by 3. You can see, just by comparison here, this whole term is t sub e divided by 3. So the answer is A. Okay, so I proved this by kinematic equations and by knowing the facts of projectile motion. You always remember the facts, and then you can solve, any question regarding projectile motion if you know the facts. Okay, I hope it was helpful. Feel free to leave any comments, likes, subscribe to the channel if you see it's helpful, and have a nice day.